Whoever said the journey was more important than the destination probably wasn't talking about carbon footprints, but they may as well have been. The truth is, transportation, moving people and products around, is responsible for about 14% of global greenhouse gas emissions, and in the US, it's the single largest source of CO2. But how do we travel, ship goods, or run our industries in a more ecologically friendly way? Today, we're going to go beyond electric cars and public transportation and see some of the groundbreaking new technologies that you may not have heard of. We'll visit the world's brightest scientists, engineers, and inventors and see their bold new ideas for technologies that help rescue the planet. And we'll learn how they're using cutting-edge simulation software, like the kinds developed by Ansys, to speed up development, reduce costs, and generally make sure we get these vital transportation solutions as fast and as efficiently as possible. When it comes to electric cars, we've come a long way, literally miles. But the fact is, transportation remains responsible for nearly a quarter of global emissions, and personal vehicles are just one contributing factor. Heavy machinery and rail, for example, still largely rely on internal combustion engines to operate. Turntide is looking to change that. With a diversified portfolio of solutions in electrification, energy storage, and electronics, Turntide seeks to expand the decarbonisation of transportation beyond the humble car and accelerate the world's transition from fossil fuels.
Batteries are living things, so when we look inside this and there's a cell, it's a chemistry.
Chris Pennison has developed a reputation for delivering high-performance manufacturing. His mastery over processes has put Turntide in a position to deliver industry-leading electrification solutions that are both environmentally and economically sound. So I think when most people think about electric vehicles, their first thought is might be a Tesla or a Nissan Leaf, a car, right? Yeah. But you're not doing that, are you? You're looking more broadly. Could you tell me about that?
Absolutely. What we're really interested in is what we call the long tail of electrification. So everything else that we know that will need to be electrified, from construction vehicles, agriculture, autonomous guided vehicles, marine, aerospace, everywhere that needs to be electrified but maybe isn't as advanced on the journey that the OEMs and the passenger car market is really our target.
Okay, so say I was a customer and I had, I don't know, a construction vehicle. What would be the process then of me talking to you and saying, hey, I want this electrified? What would you have to consider, and what are the challenges involved in that?
What we have to understand is what the capacity and the working requirements that we can offer you are. So you get asked an awful lot of questions. Duty cycles, how often do you want to charge it? What will your customer use it for? Is it going to be used for 23.5 hours a day? Or is it going to be used for 8 hours a day? And then how quickly do you want to charge it? Well, that puts different types of challenges into the battery. So you have to try and understand that. And then we would say, right, this is how I think we can give you what you want.
So how do you actually do all of this?
For me to be able to say to you, I can give a customer 8 years here or 5 years here or 2 years, lots of simulation. So again, before we even get to even saying, this is what you want, we can run the simulation. We can then do some of the design work. We can do the design to see if actually what we think will work. We then step that through with the team that we've got here to take the simulation data, we'll model it, then we'll hard model it. So we link it goes all the way through to the bit that actually when it ends up like this and it goes to the customer, it's gone through various iterations to get to the customer, to then, and to give you, if you're the customer, that confidence that it's going to actually do what it says it will do on the tin.
This is a bespoke designed cooling radiator.
Okay.
So that's basically blowing cold air through the cells and recirculating the
So
background.
what sort of temperature range then did you have to keep them within?
We're trying to target 25 degrees purely
Celsius.
just to make sure that the cells don't degrade. Basically what we've got inside of here, these are the battery cells. So we've got 22 of them that will fit in basically 2 stacks. We've got our own PCB design, which is the battery management system.
Rather than then building everything, run the simulation, make sure, can we still get everything that we're trying to do in that same envelope with the weight that we're allowed before we actually start to physically, cut steel to a point really. And what you've got here is the battery pack. So if you remember what he was showing you the modules. So this is in effect the fuel tank. So this is the cell modules. The cooling system at the bottom here.
Yeah.
And then what you've got on the top is the brain and the battery management system. But then this is the output of all of, in effect, 2 years work to get to this stage. And it's already been simulated for life, it's already been simulated, so we've done, you asked me about safety, so we've already done fire testing on these to make sure it reaches all of the correct, accreditation, so we've already done that. We're now at a point where these are in test vehicles, because now you've got to build miles up, and there's a year of testing on that before you even get to the production bit. This is the last part, so if you think about it, we've had raw material come in, we've built it, we've followed the process, we've charged, we've discharged, we know it's all good, then all the customers need to have, depending on on who they are, their language put on their software, and that's what we do here.
Right.
So this then really brings them to life. This really allows customers to do. To your question to me, what will I do with this when you send this to me? Well, once I've put the language on, once we've done all of our checks, once we've got all that, you will be able to then install it into your vehicle or whatever process you're using to allow it to work. So this is where it all ends up. After everything we've seen, this is the niche end of the market. So batteries that we've developed then go into this vehicle.
Awesome. So what happens, seeing as we're at the end, what happens to those batteries once you've used them?
Okay, so we're not quite at the end. So we get a life out of the batteries that are in this vehicle or our other vehicles, and we call it end of first life. So then we take the batteries back. We then have a secondary use for them, stationary energy storage, or we move them to another application. We put new batteries in here, the vehicle's as it was, and it'll run as normal, and then we continue to use the batteries.
So yeah, show me what this car does.
Okay, so we're ready to go?
Absolutely. It's so quiet.
This is quiet.
Yeah.
And now we're ready to go.
It is incredibly quiet actually. I was expecting it to be.
I'm going to give you a little squirt along here now.
Oh
ready?
yes, let's
Right,
do it.
let's
Yeah.
go.
Oh, that's amazing. In 1903, Wilbur and Orville Wright changed the world forever with a 12-second powered flight at Kitty Hawk. Just 66 years later, a man walked on the moon. Looking back at that history, our pursuit of aviation has been nothing short of incredible. But now we know that it comes with a cost. The fact is, air travel alone pumps over 1 billion tons of greenhouse gases into the atmosphere every single year. And as the world heats up in response, we need a solution now more than ever. So how do we decarbonize our aircraft? Well, MagniX is exploring how electrification can be applied to aviation, presenting a proven capacity to power a diverse range of aircraft and driving the world's transition towards electric flight. An author and inventor with 5 patents to her name, Sarah Rogier has worked extensively on the development of electrical machine technologies for aircraft. Here at MagniX, she leads electric propulsion system development, focusing on the design and delivery of electric power units for carbon-free flight. When most people think about electric aviation, they're going to be thinking about your big international jets.
Yeah.
But you're doing something entirely different. Are you seeing this as a potential replacement for car journeys?
Yeah, definitely. I mean, we're flying, for example, the Beaver. Now he achieved half-an-hour flight and is covering distances that usually are covered by car journeys.
Tell me about the broader context. Why are we trying to electrify aviation?
Yeah, of course, one of the main reasons would be the environmental impacts. Short-haul flights are the most polluting one. So if we are going to replace the fuel engine with electric engine, we are literally cutting down all the emission coming from the short-haul flights.
I know that aviation is one of these industries which is often held up as one of the hardest to decarbonise.
Yes,
but clearly you're making great steps to doing that.
Yeah, I think the main chance that we need to give to aviation is prove that we can do this. So if we have the right infrastructure, if we have all the certification done, then if we can prove that we can fly and it's easy to make it, then we can move even faster.
So as with all technological solutions to problems, I'm guessing there's a lot that can potentially go wrong. So how do you mitigate against that and predict how your technology will work?
Yeah, we have to start from simulation. For example, when we design the motor and we design the entire PU, we of course have to start from finite element simulation to predict the electromagnetic behavior of the motor, then moving to thermal simulation to see how can we extract the heat from the losses produced by the motor. Then we have to integrate all the rest, for example, the control, which is part of the inverter behavior. We have to simulate everything at system level. And then we move to hardware in the loop. So we simulate part of the system and the rest is hardware. And finally we move to the completely integration of the EPU with the final propeller configuration that we're gonna have on the aircraft. There's no more calculation by hand you can do. We need to have finite element simulation, even from the mechanical part. We have to have simulation to simulate the stress around the motor and the mounting parts. Everything is basically done by simulation. Like we cannot fail this.
Obviously this is having a massive impact on emission reductions, or has the potential to at least. Are there any benefits beyond the environmental?
Mainly costs. A ticket, instead of costing $500 will cost $50 estimated, and also like noise. You can have aircraft close to your hometown, let's say, and then you won't have this huge noise that you're having if you have a fuel engine. I mean, the electric airplane will be much quieter than that.
Reliable and eco-friendly, the bicycle has been around for quite some time. But what if you've suffered an injury, live next to a really steep hill, or have a longer commute? Over the past decade, we've seen these once impossible uphill climbs conquered by the e-bike. That is, a bicycle supported by an electric powertrain. But how do we make this tech lightweight, powerful, versatile, and accessible to everyone? That's just what Bimotal is doing.
Wildest dreams into a world basically genesis for this idea was actually an accident. So I had a ski injury, and that led to me not being able to ride the bike trails I loved riding.
Growing up in the tech-rich culture of Silicon Valley, it's hardly surprising that tinkering with electronic devices became an early hobby for Toby Rico. Working on EVs by day, Toby Rico spent his evenings and weekends researching to find the most efficient combination of power, weight, and versatility in an electric assist system for bicycles. The result of hours of research and entrepreneurial spirit is right here, Bimotal.
I started staring at my bike literally hours every night after work. And eventually the idea came to me. I was like, wow, you can put a lot of torque through a disc brake. I wonder if you can change the direction and get some propulsion that way.
You're effectively, as I understand it, creating a device that you can attach to almost any bike and it becomes an electric bike. So how does it work?
This is the Bimotal Elevate, and basically the way it works is we have a motor here, and then there's a multi-stage gearbox in here, and that lets us reduce the torque on the motor so we can make the whole thing smaller. And then we have a proprietary gear here, and this drives torque through the bike's disc brake. And so in order to make a bike electric, we have to swap the disc, add a couple bolt-on mounts over the brake caliper, but basically any brake mount can handle a lot of torque, so it's a great way to make most bikes electric, without any real modifications.
Can I have a look?
Absolutely. Yeah.
I mean, my first impressions are it's much smaller than I was thinking. So this is attached to every bike, or what are the limitations?
Yeah, so right now we're launching it and targeting more mountain bikes because there's a much higher rate of compatibility there. But eventually we're trying to make it compatible with pretty much any bike that has a disc brake. And the general trend of the market is actually moving towards disc brakes. So this is a stock brake caliper. This is a sort of stock bike position. This one aluminum piece is designed by Bimotal, and then these quick connects and connector also designed by Bimotal. So it's latching onto these two studs here, and then this is the electrical contact custom connector we also designed, and so that lets you take it on and off rapidly.
That was very quick. So how much power does it generate?
The Elevate system can actually do even more than 750 watts. What a lot of people don't know is they think these systems are power limited, but it's actually torque that's the challenge. So providing high torque is something that's difficult to do in a small package.
So let's talk about the bigger picture here, because obviously driving cars is still kind of the go-to form of transportation, and by and large those cars are producing a lot of CO2. Clearly, if we cycled more, that's got to be part of the solution.
If you look at sort of how much CO2 is generated, road transportation is still the single biggest block and sub-block. The gas car is about 250 grams of CO2 per mile. An electric car is about 50 grams of CO2 per mile. So that's a 5 times reduction. You get down to an e-bike, it's about 5 grams. And so that's another 10x better than an electric car. And step one is making bikes more fun. So the Elevate system, you get on this thing, it's just a blast. Improving the metrics of the bike system, the range, the weight, reducing cost by making it so you don't have to get a whole new bike, you can add this system. All these things will kind of add up and make bikes a little more approachable. So we have this cloud of motors. We do magnetic simulations, we do thermal simulations, we look at noise, we look at any other limits of material selection, how we can wind the motor. So we put that all together, come up with a few good motor candidates. And then the next step, which is even more exciting, is we get to take this into a real heavy-duty simulation tool called Ansys MotorCAD, and basically map flux lines of how the magnetics work on the motor. We can check the thermals of the motor. We can also check and get an early estimate of how loud the motor might be.
A bottle-sized battery pack and ultra-lightweight motor allows even the most casual cyclist to generate over 750 watts of power, enough to run your microwave. But how does this technology handle a real challenge, like a steep incline, a rather common sight here in Northern California? Let's find out. we will not slow down. As we continue to advance our capability to travel greater distances and at greater speed, it is crucial that we do so in ecologically friendly, carbon-neutral ways. Which means our brightest scientists and boldest innovators must be armed with the advanced tools and technology necessary to expand what's possible, predict the future, turn wildest dreams into reality, and rescue our planet.